Badminton is a racket sport played by hitting a shuttlecock over a net. Think tennis with a volleyball net, but the ball never bounces, and the ball is not a ball, it's a shuttlecock. Drag for both synthetic and feather shuttlecocks is caused primarily by the flow around it and the air resistance that occurs as the shuttle moves through it. For a shuttlecock, this occurs at Reynolds numbers from 13,000, which applies to a shuttle moving around 3 meters per second, to 200,000, which applies to a shuttle moving around 45 meters per second. Shuttlecocks have the lowest ballistic coefficient of any airborne sporting projectile. The ballistic coefficient is a measure of an object's ability to overcome air resistance. Hence, the shuttlecock exhibits an extremely large in-flight deceleration, shown by the relatively slow speed when the shuttle falls back. There are two primary forms of drag that affect a shuttlecock in motion: form drag and viscous damping, otherwise known as skin friction. Form drag dominates most of the drag force experienced by the shuttlecock.
Moving on to discussing the drag due to the pressure differential, we'll look closer at the synthetic shuttlecock. Looking at the diagram, we have labeled a windward side and a leeward side. The windward side is where the air passes along the outside of the shuttlecock, and the leeward side is where the air goes into the skirt of the shuttlecock behind the cork. The design of the shuttlecock enables drag due to the pressure differential between the high pressure region on the windward side and the low pressure region on the lee side. The high pressure is caused by fluid, air, stagnating on the surface, and the low pressure region is caused by the high velocity fluid moving through the holes in the skirt, which we know from Bernoulli's equation is inversely proportional to the pressure. Force is acting from a high pressure region to a low pressure region, which in our case is opposing the velocity of the shuttlecock, the definition of a drag force. Finally, small regions of potential separation of the flow lead to a low pressure wake and region off the back of the shuttlecock. This pressure differential, labeled with pink triangles in the separation region near the rear of the shuttlecock, also causes damping in the motion of the shuttlecock, for the same reason of how the force is acting from a high pressure region to a low pressure region along the shuttlecock, which is opposing its direction of motion, aka its velocity.
What is a vortex? A vortex is a region of locally rotating fluid that imitates solid body rotation near the center, meaning that velocity increases proportionally with radius until a certain boundary, where the fluid transitions to imitate a point vortex, where velocity varies inversely with radius from the center. Vortices form along the windward side of the shuttlecock in a small layer right above the surface, due to a combination of viscous forces from the feathers and the rotation of the shuttlecock. When these vortices are shed, it increases the turbulence of the region behind the shuttle and creates further drag.
One might ask, why does the shuttlecock rotate? Well, the shuttlecock rotates due to the arrangement of feathers on the cork. The slight angle the feathers form with each other, as well as the geometry of the feathers, induce a moment around the center of the shuttlecock. In addition, the relatively high density of the cork, compared to the feathers, forces the shuttlecock to move towards its most stable configuration, which is leading with the cork. This is shown by the rapid speed at which the shuttlecock turns around after being hit. It takes an average of 20 milliseconds to turn around and 80 milliseconds to stabilize while in midair.
Rotation brings angular momentum into play, and as a result, the shuttlecock behaves like a top rather than a stationary object. The rotation means that every particle that makes up the shuttlecock, especially the ones towards the ends, which are the most affected by instabilities in the flow, have a centripetal force that dominates other forces acting on the shuttlecock. This means perturbations in the environment due to wind and such have much less effect on the movement of the shuttlecock.
Analogies of the shuttlecock can be made to other rotating systems. Rifles and barrel rifling involves a groove along the inner part of a gun barrel to give the projectile, a bullet, a spin about its major axis upon exit, stabilizing it. Similarly, if we look at the diagram, a thrown football or a spiral also has a spin about its major axis that causes a stable rotation and less separation of the fluid off of the back end. On the other hand, a kicked football often rotates about an unstable axis, where more separation off the backside leads to a higher drag force from the fluid. Also noted, drag coefficients of the shuttlecocks have been experimentally determined to be nearly constant and not change with Reynolds number, for Reynolds number from 13,000 to 200,000, as mentioned before in the drag section of the video. This is consistent with trends seen for spears and other bluff objects that experience vortex shedding.